Something out there, in the deep and silent black, is changing course, and its new target could be us, the interstellar visitor known as 3I Atlas. Once written off as just another frozen wanderer tumbling through the void, has begun to accelerate, subtly, steadily, in a direction that simply shouldn't be possible. According to a series of chilling, independent analyses based on Avi Loeb's report of a non-gravitational acceleration near its closest approach to the Sun, if this push continues for just 50 days, it could shift its velocity by a staggering 86 meters per second, enough to perfectly line its trajectory up with the orbital position of our planet, Earth, on December 19th, 2025. Now let me be clear. This is the pivotal question, the fork in the road for all of human history. Is this just physics? The random chaotic jetting of a comet? A coincidence of dust and sunlight? Or is it propulsion? A deliberate, calculated maneuver? And right alongside this impossible motion, there's a signal, a frequency, 1.4 GHz. Faint, rhythmic pulses, almost mathematical in their precision, echoing through the void. It sounds almost like a reply. Could this be coordination? A handshake in the dark between the object and something else? Stay with me, because by the end of this investigation, you will understand exactly why some of the world's most brilliant and skeptical scientists are whispering the unthinkable. 3I Atlas isn't just passing by. It may be maneuvering. It may be aiming. It may be coming for a visit. If this mystery has you hooked the way it has me, if you feel that primal chill of curiosity and awe, then you need to be part of this journey. So, let me know right now, where in the world are you watching from, and what time is it there? This is a global event, and your perspective is part of the story. Drop a comment below, and make sure you hit that subscribe button and ring the notification bell. You are the reason we can chase stories like this, and by subscribing, you guarantee you won't miss a single second of this story as it unfolds in real time, right here. Thank you for having our back. This is part 1. The claim has been broken. The anomaly is real. Something is coming. To understand the profound strangeness of 3I Atlas, we must first grasp what it represents. This is not an asteroid from our own asteroid belt, not a comet from the distant Oort cloud that still orbits our sun. This is an outsider. Its trajectory is hyperbolic, a term that signifies the ultimate freedom or the ultimate indifference of the cosmos. It is moving too fast to be captured by the sun's gravity. It came from somewhere else, a place we can only point to with telescopes and guesswork, and it will leave again, vanishing back into the interstellar deep. This is the hallmark of a true interstellar traveler, and 3I Atlas is only the third such object we have ever confirmed. The first was the enigmatic cigar-shaped Oumuamua in 2017, which sparked endless debate with its own slight, unexplained acceleration. The second was Borisov in 2019, a relatively normal-looking comet that behaved largely as expected. Now we have 3I Atlas, and it is its behavior that places it in a category of its own, forcing us to ask uncomfortable questions. Its perihelion, its closest approach to the Sun, occurred around October 30th, 2025, at a distance of about 1.36 to 1.4 astronomical units, placing it roughly within the orbit of Mars. Its predicted closest approach to Earth is on December 19th, 2025. But here is the first crucial detail that separates fact from sensationalism. The distance will be a vast 1.8 astronomical units, approximately 270 million kilometers away. To put that in perspective, the Moon is only 384,000 kilometers from us. This object will pass at a distance equivalent to 700 times the Earth-Moon distance. This is not a close call by any conventional or even planetary defense standard. It is a distant passage. Yet the anomaly remains, a ghost in the machine of orbital calculations. The object was not where it should have been. Astrometry data from the Jet Propulsion Laboratory and the Atacama Large Millimeter Array showed a tiny but significant offset of about 4 arcseconds, a minuscule angular shift. But when you are tracking something across millions of kilometers, it is a glaring red flag on the map of the sky. The core of this mystery is the non-gravitational acceleration. This is not a magical term. It is a precise scientific description for when an object moves in ways that gravity alone cannot explain. In the vacuum of space, where the laws of motion are supposed to be pristine and predictable, something else is pushing on 3I Atlas. The measured acceleration is a tiny 0.02 mmMATS S2, a force about 150,000th of Earth's gravity. It sounds insignificant, almost laughably so. But in the frictionless environment of space, over days and weeks, tiny pushes add up to monumental changes in velocity and position. Avi Loeb calculated that this level of sustained thrust would require a tremendous release of energy and material. If the cause is outgassing, the sublimation of ice into gas, creating jets that act like tiny natural rocket engines, then the rate of mass loss must be substantial. His calculations are staggering. For an object with an estimated mass of tens of billions of tons, it would need to lose at least 1/6 of its total mass over the course of about a month to produce that 0.02 ms2 push. Let that sink in. Imagine a mountain in space evaporating 1/6 of itself in just 30 days. This should be a spectacular, unmistakable event. It should produce a massive glowing cloud of gas and dust around the nucleus, a visible coma, and a brilliant tail stretching millions of kilometers, pushed by the solar wind. This is what comets do. This is what we expect. But with 3I Atlas, the visual evidence is ambiguous. There are reports of a jet structure, possibly directed in an unusual way, and its color is described as bluer than the sun, potentially indicating ionized carbon monoxide. But the definitive massive coma, it hasn't been conclusively observed. The engine is running, but we can't see the exhaust. This is the first major crack in the natural explanation, the first hint that our default assumptions might be leading us astray. This is where the scientific data meets human imagination and the powerful, often distorting lens of social media. An independent researcher took Avi Loeb's numbers and performed a straightforward calculation from classical physics. Acceleration multiplied by time equals a change in velocity, a constant acceleration of 0.02 ms2 sustained for 50 days, which is for 320,000 times. Seconds does indeed yield a delta V of approximately 86.4 ms. The math is impeccable. Furthermore, this velocity change would also result in a significant displacement of the object's position. The formula for displacement under constant acceleration shows a shift of about 187,000 kilometers, roughly half the distance between the Earth and the Moon. In the precise geometry of orbital mechanics, such a shift is far from trivial. It could theoretically alter a flyby distance, change an arrival time, or, under very specific conditions, convert a distant pass into a closer one. This is the arithmetic foundation of the dramatic claim that 3I Atlas is lining up with Earth. But here is where the chain of assumptions begins. Each link a potential point of failure. The calculation assumes the acceleration continues unabated for 50 days. We have a measurement from a specific point near perihelion. We do not know if it persists. Outgassing typically varies with solar distance, weakening as the object moves away from the sun's heat. The calculation also assumes the acceleration is applied in exactly the right direction. In space, direction is everything. A push sideways, forward, or backward relative to its velocity vector would have vastly different effects on its trajectory relative to Earth. A prograde burn speeds it up, changing when it arrives. A retrograde burn slows it down. A radial push changes the shape of its orbit. Without knowing the vector, any prediction of an Earth intercept is pure speculation. Finally, the timing must be perfect. Earth is a moving target, traveling at 30 km/s. To orchestrate a rendezvous requires a precise understanding of orbital dynamics that borders on prescience. The social media claim assumes all these factors, persistence, perfect direction, and flawless timing, are aligned. It is a house of cards built on a foundation of real but incomplete data. Let us now confront the central claim with the cold, hard reality of the official orbital calculations. According to NASA and the European Space Agency, whose models incorporate the full suite of gravitational perturbations and the most precise astrometric data available, 3I Atlas will make its closest approach to Earth on December 19, 2025, at a distance of 1.8 astronomical units, or about 270 million kilometers. This is not a number open to interpretation. It is the result of the world's most advanced orbital mechanics software. For context, an object is classified as potentially hazardous if it comes within 0.05 astronomical units, about 7.5 million kilometers of Earth. 3I Atlas will pass at more than 30 times that threshold. Both NASA and ESA have stated explicitly, unequivocally, that this object poses exactly zero threat to our planet. So, could the theorized 86 ms velocity change alter this safe passage into a dangerous one? The answer is a nuanced yes and no. Yes, in principle. A delta V of that magnitude could shift the trajectory by hundreds of thousands of kilometers, as we calculated. But no, it is astronomically insufficient to close a gap of 270 million kilometers. The object is moving at a hyperbolic velocity of roughly 60 km/s, 60,000 ms. An 86 ms change is less than 0.15% of its total speed. To shift the missed distance from a safe 270 million kilometers to 0 direct impact would require a velocity change on the order of several kilometers per second, applied with surgical precision months or even years earlier. The geometry itself is a formidable barrier. Think of it as trying to thread a needle from 1,000 miles away, while both the needle and the thread are moving at hypersonic speeds. The direction of the thrust is, again, the critical unknown. A push perpendicular to its path might shift its trajectory laterally without bringing it significantly closer to Earth's orbital position at the crucial moment. The official models from space agencies, which have access to the full data and account for all known forces, show a safe passage. If there were even a fractional chance of impact, the global planetary defense network would be in a state of high alert. For 3I Atlas, the alarm bells are silent. The reality check is clear. The Earth intercept scenario is a geometric and kinetic improbability of the highest order. The definitive answers will not come from arithmetic on social media, but from the patient, meticulous work of telescopes pointed at the sky. The next few months represent a critical, narrow window of opportunity. Having passed perihelion in late October, 3I Atlas is now on its outbound journey, moving away from the Sun and toward its December 19th close approach to Earth. As it emerges from the Sun's glare, it becomes a prime target for the most powerful observational tools humanity has ever built. This is a global, coordinated scientific campaign. The Hubble Space Telescope is capturing high-resolution images in visible and ultraviolet light, scrutinizing the object's surface and any surrounding material for structure. The James Webb Space Telescope, with its unparalleled infrared sensitivity, is analyzing the heat signatures and chemical composition of any gases, searching for the spectroscopic fingerprints of water, carbon monoxide, methane, or more exotic compounds. On the ground, observatories like the Very Large Telescope in Chile and the Keck Observatory in Hawaii are contributing their immense light-gathering power, using adaptive optics to cancel out atmospheric blurring and see with stunning clarity. Radio telescopes across the globe are listening, not just for the alleged 1.4 GHz pings, but for any natural radio emissions that could reveal plasma interactions or other physical processes. There is even a fascinating cosmic coincidence. The European Space Agency's Jupiter Icy Moons Explorer, JUICE spacecraft, will pass within about 64 million km of 3I Atlas in early November. While not a dedicated flyby, its instruments might still gather valuable data from a relative proximity that we cannot achieve from Earth. This is all hands-on-deck astronomy, a race against time as the object will begin to fade from view after December, heading into the outer solar system and back into the eternal night from which it came. The purpose of this intense observational campaign is to test a clear set of competing hypotheses. The scientific method demands that we make predictions and then see if reality conforms to them. For 3I Atlas, the predictions create a fork in the road, leading to two very different futures of understanding. The first path is the natural outgassing hypothesis. If this is correct, the predictions are straightforward. Telescopes should soon detect unequivocally a large coma and a tail. Spectroscopy should reveal abundant volatiles water, CO, CO2 being released at a rate consistent with Loeb's calculated mass loss of billions of tons per month. The acceleration itself should correlate strongly with distance from the Sun. As the object moves farther out and cools, the outgassing and thus the thrust should measurably decrease. This would be the comforting conclusion. 3I Atlas is a weird, hyperactive comet, but a comet nonetheless. The second path opens if these predictions fail. If observations show minimal to no coma, if the gas and dust are absent, despite the persistent acceleration, then the natural hypothesis weakens catastrophically. If the acceleration continues or even increases as the object moves away from the Sun, defying the logic of solar heating, that is a major red flag. This is when the door to more exotic explanations swings wide open. The measurements to watch are the astrometric residuals, the precise differences between where the object is actually observed and where a gravity-only model predicts it should be. These residuals will map the true magnitude and direction of the non-gravitational force. High-resolution imaging will analyze the morphology of any jets. And of course, radio observatories will deliver a simple binary result. Either there is a structured, artificial signal, or there is not. The coming weeks are a process of elimination, a grand experiment conducted on a solar system-wide scale. Let us delve deeper into the natural explanation, for it is the default position of science to seek answers within known physics before venturing beyond. Comets are essentially dirty snowballs. Their nuclei are a primordial mix of ice water, carbon monoxide, carbon dioxide rock, and complex organic molecules. As they approach the sun, the ices sublimate, turning directly from solid to gas. This escaping gas carries dust with it, forming the coma and tail, and crucially, it imparts a thrust on the nucleus. This is a well-understood rocket effect. For 3I Atlas, the challenge is the scale. Avi Loeb's momentum conservation calculation is not controversial. To produce a force of 0.02 mmS2 on a 30 billion-ton object requires ejecting mass at a tremendous rate. The numbers suggest a loss of about 5 billion tons per month. This is not a gentle steaming. It is a violent, continuous eruption. So where is the smoke? The observational ambiguity is the central problem. There are potential excuses, or more accurately, complexities. Cometary activity is not always uniform. It can be episodic, driven by the object's rotation exposing fresh ice to sunlight, or by the sudden collapse of a crusty surface layer. Perhaps the outgassing is highly concentrated in a few powerful jets, which might make the overall coma less obvious from our distant viewpoint. The unusual blue color could point to a composition rich in carbon monoxide, which sublimes more easily than water ice, and could produce a gas that is less dusty and therefore less visible. Some images hint at an anti-tail, a feature that appears to point toward the sun, which can be a trick of observational geometry, but is still rare. An interstellar comet, forged in a completely different stellar environment, could easily have a composition and behavior that falls outside our experience with solar system comets. The natural explanation is plausible, but it is strenuous. It requires that several unusual factors align perfectly. It asks us to believe we are witnessing a perfectly natural, yet extraordinarily dramatic cometary outburst that just happens to mimic the characteristics of controlled propulsion. It is possible, but the burden of proof is growing heavier with each passing day that fails to show the expected colossal cloud of gas and dust. Now we venture into the territory that captures the imagination and sparks both fascination and skepticism. The technological hypothesis. What if the acceleration of 3I Atlas is not natural? What if this object is not a comet, but a relic, a probe, a piece of technology crafted by an intelligence from another world? Avi Loeb and his colleagues have formally published a paper asking precisely this question. Is the interstellar object 3I Atlas alien technology? This is not presented as a conclusion, but as a serious scientific inquiry into what we can and cannot rule out. The argument rests on a convergence of anomalies. First, the non-gravitational acceleration without the definitive, massive outgassing that should accompany it. Second, the object's substantial size and mass, which makes accelerating it through any means a significant engineering challenge. Third, the trajectory itself. Some statistical analyses suggest its path through the inner solar system and its alignment with the plane of Earth's orbit are somewhat unusual for a purely random interstellar visitor. Let's consider the energetics. To sustain a thrust of 0.02 mmS2 on a 10^13 kilo object requires a continuous force of about 200,000 newtons. This is equivalent to the thrust of a small but powerful rocket engine, burning continuously for weeks. If this is not outgassing, what could it be? A solar sail would need to be kilometers across and perfectly reflective. An ion drive or some form of nuclear propulsion is conceivable. The unverified claims of 1.4 GHz pings add a layer of narrative, placing the object in the waterhole frequency, a logical choice for interstellar communication. Of course, there is no public, peer-reviewed detection of such signals, and their absence is a major point against this hypothesis. But if we entertain the idea, what could 3I Atlas be? A dormant probe, adrift for eons, now reactivated by the warmth of a star. An active reconnaissance vehicle, deliberately adjusting its course to survey the inner planets. Loeb has even referenced the dark forest hypothesis, suggesting that a cautious civilization might send silent, observant probes rather than announcing their presence with loud radio signals. This is a chain of speculation, each link weaker than the last. But the core anomaly, the push without the plume, remains, keeping the technological hypothesis alive, if not yet well. The story of 3I Atlas did not break in a scientific journal. It erupted on social media. In mid-October 2025, posts on the platform X began to circulate, authored by an independent researcher. They laid out the compelling arithmetic: the 0.02 MSS2 acceleration, the 50-day burn, the 86 MES delta V. So far, this was just a repackaging of Avi Loeb's data. But then, the narrative escalated. The researcher asserted that this acceleration was not random. It was intentional. The object was maneuvering, performing course corrections, aiming itself at Earth. The posts mentioned 1.4 GHz pings detected near Mars, spoke of handshakes between the object and some unknown entity, and framed the entire event not as a scientific curiosity, but as an alien probe targeting our world. This is a classic case of how narrative is layered onto data. The data, the acceleration, is real. The arithmetic, the velocity change, is correct. But the interpretation, the intent, the targeting, is a creative leap, an assumption piled upon an assumption. The psychology at play is powerful. Humans are pattern-seeking creatures. We are wired to see agency and intention, a trait that served us well when discerning a predator in the bushes, but can lead us astray in the random, impersonal realm of cosmic phenomena. An unexplained acceleration becomes a sign of intelligence. The lack of an immediate, comforting explanation from authorities is seen as a cover-up. The narrative becomes self-reinforcing, immune to contradiction. This phenomenon is not new. Oumuamua went through the exact same cycle. Scientists admitted they were puzzled, and the internet filled the vacuum with aliens. The involvement of figures like Avi Loeb, who deliberately and publicly entertains exotic possibilities, provides further fuel, even as he carefully frames it as hypothesis, not conclusion. Mainstream media often amplifies the most dramatic angle with headlines screaming alien probe, even when the accompanying article is more measured. The result is a blurred line, where a measured scientific anomaly and an unsubstantiated claim of alien contact are given equal weight in the public consciousness, creating a storm of excitement, fear, and misinformation. While the evidence points overwhelmingly to a safe passage, it is a valuable exercise to explore the ultimate what if. Let us engage in a thought experiment. What if every fragile assumption held? What if, against all odds, 3I Atlas possessed a propulsion system of unimaginable power and somehow altered its course to directly intersect Earth? The parameters are terrifying. Size estimates for the object range up to several kilometers in diameter. Conservative mass estimates place it at over 30 billion tons. It is moving at a hyperbolic speed of roughly 60 km/s. The kinetic energy of such an impact is almost beyond comprehension. Plugging the numbers into the formula, the energy release would be on the order of 1.35 x 10 times 22 joules. Converted into megatons of TNT, this is approximately 3.2 million megatons. For comparison, the Tsar bomber, the largest nuclear weapon ever detonated, was 50 megatons. The impact of 3I Atlas would be over 60,000 times more powerful. The consequences would be an extinction-level event. The object would strike the atmosphere at nearly full speed, punching through to the surface in seconds. The instantaneous release of energy would vaporize the impactor and a vast volume of the Earth's crust, blasting it into the upper atmosphere. A fireball would incinerate continents. The shockwave would flatten everything for thousands of kilometers. If it struck an ocean, tsunamis thousands of meters high would scour coastlines around the globe. But the immediate destruction would be just the beginning. The dust and aerosols injected into the stratosphere would encircle the planet, blocking sunlight for years. Global temperatures would plummet, photosynthesis would halt, agriculture would collapse, and a global famine would ensue, likely ending human civilization and most complex life on Earth. This is a scenario on par with the impact that wiped out the dinosaurs 66 million years ago. This thought experiment is not a prediction. It is a tool for understanding the stakes of planetary defense and the importance of accurate science. It also highlights the sheer implausibility of the intercept scenario. To achieve such a collision would require a delta V thousands of times greater than the speculated 86 MES, applied with godlike precision. The worst-case scenario is a useful spectre to motivate vigilance, but it is not our reality. The story of 3I Atlas is about more than one object. It is a window into a new era of astronomy. Before 2017, with the discovery of Oumuamua, interstellar objects were theoretical. Now we know they are real, and they are visiting our solar system with a frequency we are only beginning to appreciate. 3I Atlas is the third confirmed visitor, but future telescopes like the Vera C. Rubin Observatory, which will begin full operations soon, are expected to find one or more every year. This changes everything. These objects are physical samples from other star systems. By studying them, we can perform remote geology on planetary systems light years away, analyzing their composition to understand the diversity of planet formation across the galaxy. Oumuamua taught us that they can be strange, showing acceleration without visible outgassing. Borisov taught us that they can be perfectly normal, behaving like a typical comet. 3I Atlas sits in the middle, showing us that the spectrum of normal is wider than we imagined. This new reality also has profound implications for planetary defense. Deflecting an interstellar object is a far greater challenge than deflecting a solar system asteroid. They are faster, giving us less warning and requiring more energy to divert. They appear suddenly, and their observation windows are short. Our current infrastructure, designed for objects whose orbits we can predict years in advance, is not well suited to handle interstellar interlopers. This motivates the development of rapid response mission architectures, like the ESA's Comet Interceptor, and more powerful detection networks. Furthermore, if 3I Atlas or any future object were to show signs of artificiality, it would revolutionize the search for extraterrestrial intelligence, SETI. It would shift the paradigm from listening for signals to looking for artifacts, physical evidence of other civilizations that may have sent probes, either actively or as relics of a bygone era. 3I Atlas, therefore, is a wake-up call. It reminds us that our solar system is not an island, but a port in a cosmic ocean, subject to visits from driftwood and potentially ships from shores we have yet to map. In 2025, our ability to analyze celestial objects is being supercharged by artificial intelligence. New AI-driven tools are transforming astrometry and orbit prediction, bringing a new level of precision and pattern recognition to the mystery of 3I Atlas. Tools like OrbNet, a neural network trained on decades of asteroid and comet data, ingest astrometric observations and compare them to gravitational models. It doesn't just flag residuals, it suggests potential causes based on patterns it has learned, outgassing, radiation pressure, or even unknown thrust. Another tool, Astro AI, developed by the European Space Agency, uses reinforcement learning to simulate millions of possible trajectories, testing scenarios far too numerous for human astronomers to calculate. Researchers have already used Astro AI to put the social media claim to the test. They input the observed data and asked, what would it take for 3I Atlas to achieve an Earth intercept on December 19th? The AI's answer was definitive and damning to the sensationalist narrative. The required delta V is not 86 ms, but several kilometers per second, applied months earlier with perfect vectoring. The social media claim collapses under the weight of rigorous AI-driven modeling. AI is also revolutionizing the search for technosignatures. Projects like Breakthrough Listen use machine learning algorithms to sift through petabytes of radio data, filtering out terrestrial interference and natural noise to flag candidate signals that exhibit structure or information content. If 3I Atlas were emitting the alleged 1.4 GHz pings, these AI systems would almost certainly have detected them by now. The fact that they have not is a powerful, albeit negative, data point. AI serves as a force multiplier for science, helping to refine orbits, detect subtle anomalies, and rule out implausible scenarios with computational brute force. It brings a new level of objectivity to investigations often clouded by human bias and excitement. For 3I Atlas, AI is not the judge, but a powerful expert witness, providing clarity and crushing speculation with cold, hard probability analysis. The claim of 1.4 GHz pings is one of the most tantalizing yet unverified aspects of the 3I Atlas story. The 1.4 GHz frequency is profoundly significant in astronomy. It corresponds to the emission line of neutral hydrogen, the most abundant element in the universe. This waterhole is a naturally quiet band in the radio spectrum, making it a theoretically ideal channel for interstellar communication. A universal landmark where any technological civilization might choose to broadcast or listen. In early 2025, the Breakthrough Listen project released the results of its most comprehensive survey, yet of the 1.2 to 1.8 GHz band, covering millions of stars. They found no confirmed technosignatures. setting stringent limits on how common, powerful, deliberate radio broadcasts are in our galactic neighborhood. This is the context for the 3i Atlas claim. If such pings were real, they would represent a monumental discovery. But the radio astronomy community, with its global network of sensitive telescopes and sophisticated AI processing, has reported nothing. No major observatory has confirmed a structured, artificial signal originating from the object. The silence is deafening. From an engineering standpoint, it is certainly plausible for a probe to have a radio transmitter. A nuclear power source could generate the necessary watts or kilowatts, and an antenna a few meters across could efficiently beam a signal at this wavelength. However, natural phenomena can also produce radio emissions. Comets interacting with the solar wind can generate plasma oscillations that create radio noise. The lack of a detected signal does not definitively prove the object is natural, but it removes the single most compelling piece of evidence that would suggest otherwise. The ongoing radio monitoring campaigns are crucial. They represent a test with a binary outcome. Either a signal is found, transforming the entire investigation, or the continued silence gradually buries the communication hypothesis under the weight of negative evidence. For now, the sky around 3i Atlas remains silent, speaking not in pings and handshakes, but in the language of gravity and light, which we are still struggling to interpret. We have journeyed through the data, the hypotheses, the narratives, and the technologies surrounding 3i Atlas. Let us now synthesize the key takeaways and look ahead to the critical timeline of events. First, the object is a confirmed, scientifically priceless interstellar visitor. Second, the non-gravitational acceleration is a real anomaly that demands explanation. Third, the arithmetic behind the 86 MES velocity change is correct, but its extrapolation to an Earth intercept scenario rests on a chain of unverified and geometrically implausible assumptions. Fourth, official orbital calculations from NASA and ESA are clear. A safe passage at 270 million kilometers is the definitive prediction. Fifth, the natural outgassing hypothesis is strained by the lack of a corresponding massive coma, but it remains the leading, most parsimonious explanation. Sixth, the technological hypothesis is captivating but remains in the realm of speculation due to a complete lack of confirming evidence like radio signals or non-volatile thrust. The timeline is now our guide. Perihelion is behind us, occurring on October 30th, 2025. Throughout November 2025, the object is emerging from solar conjunction, becoming increasingly visible to the world's telescopes. This is the period where the critical data will be gathered. December 19th, 2025 is the date of closest approach to Earth. It is not a date of impact, but a date of culmination for the observational campaigns. By early 2026, as 3i Atlas speeds toward the outer solar system, the data will be analyzed, papers will be written, and we will have our answers. The universe is under no obligation to conform to our desires for comfort or for drama. It simply is. The story of 3i Atlas is another step in humanity's long, humbling journey to understand our place in the cosmos. Whether it is a strange comet or something more, it has already succeeded in reminding us to look up, to question, and to marvel at the mysteries that drift through the night. To fully grasp the significance of 3i Atlas, we must look to its predecessors, the celestial pathfinders that first broke the barrier between our solar system and the galactic void. The first, Oumuamua, discovered in October 2017, was a shock to the system of astronomy. It was small, faint, and already on its way out when we spotted it. A fact that itself hints at how many such objects we must miss. But its anomalies were what captivated and confounded scientists. Its shape, inferred from its dramatic changes in brightness, was extreme. A pancake or a cigar, hundreds of meters long, but only tens of meters wide. A form unlike any known asteroid or comet in our solar system. Then came the acceleration. As it departed, it sped up slightly, a non-gravitational push that could not be explained by the gravitational tug of the sun or planets. The search for a coma, for the telltale spectrographic signs of outgassing, came up empty. Nothing was visible. This was the core of the mystery, an acceleration with no apparent propellant. Avi Loeb's light sail hypothesis, that it could be a piece of discarded technology, a solar sail from another civilization, was born from this paradox. The scientific consensus ultimately leaned towards exotic but natural explanations. Perhaps a comet made of hydrogen or nitrogen ice that could sublimate without leaving a visible trail of dust, or a fractal-like aggregate of dust particles released in a way that produced thrust without a significant coma. Then, just 2 years later, Tuai Borisov arrived. It was the antithesis of Oumuamua, a textbook comet. It displayed a brilliant coma and a distinct tail. Spectroscopy revealed familiar molecules like cyanogen and diatomic carbon. It was a comforting discovery, proving that some interstellar visitors were just that. Visitors, icy wanderers from another star, behaving exactly as our models predicted. Now, 3I Atlas stands between these two extremes, embodying the mystery of the first and the familiarity of the second, yet belonging entirely to neither. It has observable, if subtle, cometary features, yet its acceleration is strong, and the expected massive cometary envelope is conspicuously absent. It is as if Oumuamua was the cryptic first contact, Borisov the friendly follow-up, and 3I Atlas is the third encounter that forces us to decide. Were the anomalies of the first one merely flukes, or were they hints of a diversity so vast it includes the natural and the potentially artificial? The investigation into 3I Atlas is not merely a scientific pursuit. It is a philosophical and existential journey that forces us to confront one of humanity's oldest questions. Are we alone? For centuries, this question resided in the realm of theology and speculation. Now, with an object from another star system behaving strangely in our own celestial backyard, it has vaulted into the realm of tangible possibility. The potential implications are so vast, they can barely be comprehended. The confirmation that another intelligence exists, or existed, would represent the single greatest paradigm shift in human history, dwarfing the Copernican revolution, Darwinian evolution, and the discovery of the DNA helix combined. It would redefine our understanding of biology, culture, technology, and our place in the cosmos. Philosophers and scientists have long pondered the possible nature of such a civilization. Would it be benevolent, curious, and wise, a guiding hand from the stars? Or would it be indifferent, viewing us as we view ants beneath notice? Or in the darkest scenarios, would it be predatory or expansionist, a threat to be feared? The dark forest hypothesis, which Avi Loeb has referenced, posits a universe where every civilization is a hidden hunter, terrified of revealing its location for fear of being annihilated by a more advanced predator. In this grim cosmology, the great silence of the universe, the fact that we hear no signals, is not a sign of our solitude, but a sign of universal caution. If 3I Atlas were an artificial probe, its behavior, observing from a safe, non-threatening distance, would fit perfectly within this paranoid framework. It wouldn't land. It wouldn't communicate openly. It would watch and report. But beyond these grand narratives, a more profound philosophical shift would occur within us. The Earth would no longer be the sole repository of life, mind, and culture. Humanity would be forced into a cosmic humility, becoming a single member of a galactic community, real or potential. The artifacts of our civilization, from our greatest art to our most petty conflicts, would be seen in a new, perhaps jarring, cosmic context. 3I Atlas, even as a silent, distant dot of light, is a mirror forcing us to ask not only, what is it, but what are we? The dramatic, if highly improbable, worst-case scenario of an impact naturally leads to the question, what could we actually do about it? The field of planetary defense has moved from the pages of science fiction to a concrete, if nascent, global endeavor. The recent success of NASA's DART, Double Asteroid Redirection Test, mission proved a critical principle. We can intentionally alter the orbit of a celestial body through kinetic impact. By smashing a spacecraft into the moonlit Dimorphos, DART changed its orbital period around its parent asteroid, a landmark demonstration of our potential to defend the planet. However, the defense against an object like 3I Atlas presents challenges of a different magnitude entirely. DART targeted a small, slow-moving object in a stable orbit near Earth. An interstellar object is a different beast. Its speed, measured in tens of kilometers per second, is its most formidable weapon. This velocity means that any deflection mission would have to be launched with incredible speed and precision. The energy required to significantly alter the trajectory of a billion-ton object moving at 60 km/s is astronomical, far beyond our current rocket capabilities. Furthermore, the warning time for an interstellar interloper is tragically short. We detected 3I Atlas only months before its perihelion. A deflection campaign requires years, if not decades, of advance notice to plan, build, launch, and rendezvous. Our current strategy relies on early detection, finding these objects long before they become an immediate threat. This is the primary mission of surveys like ATLAS and the future Vera Rubin Observatory. For a true interstellar impact threat, our best and likely only current option would be civil defense, evacuation of the predicted impact zone, and preparation for the global climatic consequences. This stark reality underscores the importance of the ongoing observational work. By studying 3I Atlas, we are not just satisfying scientific curiosity, we are stress testing our entire planetary defense infrastructure, learning how to track, model, and understand these high-velocity visitors so that if, one day, one of them does have our name on it, we might have the decades of advance warning needed to mount a credible defense. One of the most scientifically grounded yet mind-bending exotic hypotheses for 3I Atlas's acceleration is that it is, or incorporates, a solar sail. A solar sail is a form of propulsion that requires no fuel. Instead, it uses the subtle but constant pressure of photons from sunlight. As light particles reflect off a vast, ultra-thin, and highly reflective membrane, they impart momentum, providing a tiny but continuous thrust. This is not science fiction. The Japanese Ikaros mission and the Planetary Society's LightSail 2 have successfully demonstrated the technology in Earth orbit. For Oumuamua, Avi Loeb calculated that its observed acceleration could be explained if it were a solar sail just a fraction of a millimeter thick, but perhaps hundreds of meters across. For 3I Atlas, the numbers are more challenging due to its larger estimated mass. To produce a thrust of 0.02 ms2 on a 30 billion ton object would require a sail of staggering proportions, potentially kilometers across, and of an impossibly low mass and high reflectivity. The engineering required to construct and deploy such a structure in interstellar space is far beyond our capabilities, but not necessarily beyond the capabilities of a civilization thousands or millions of years more advanced than our own. What would we look for? A solar sail would have a distinctive light curve, perhaps showing exceptionally bright and uniform reflections. Its spectrum would lack the absorption features of rock and ice, instead showing the flat, high reflectivity of a manufactured metal or polymer film. The James Webb Space Telescope, with its sensitive infrared instruments, could potentially detect the temperature of such a sail, which would be different from a dark, rocky body. If the acceleration remains constant as the object moves away from the Sun, that would be another clue. Solar sail thrust decreases with the square of the distance from the Sun, but a sail designed for interstellar travel might have other means of propulsion for the dark voids between stars. While the solar sail hypothesis is a long shot, it represents the kind of out-of-the-box thinking that is essential when confronting a genuine anomaly. It is a testable idea, and the ongoing observations will actively search for the signatures that would confirm or, more likely, refute it. If 3I Atlas is a natural comet, its very strangeness is its greatest scientific gift. As the third sample from another star system, its chemical composition is a direct probe into the conditions of its birth, a planetary system we will never visit. Every comet in our solar system is a frozen record of its formation in the protoplanetary disk that surrounded the infant Sun. Their ices contain water, carbon monoxide, carbon dioxide, methane, and ammonia, along with complex organic molecules. The ratios of these substances tell a story of temperature, pressure, and radiation history. An interstellar comet like 3I Atlas carries a completely different story, written in a different stellar nursery. The bluer-than-the-sun color reported by observers is a critical clue. This blueness could indicate a strong presence of ionized carbon monoxide, CO+, in its coma. While CO is common in solar system comets, an overabundance could indicate it formed in a much colder region of its home system, perhaps far from its parent star, where carbon monoxide ice could survive more readily than water ice. Alternatively, it could point to a system with a different carbon-to-oxygen ratio, a fundamental parameter that dictates planetary chemistry. The potential antitail, a sunward pointing feature, while likely an optical illusion caused by viewing geometry, could also indicate an unusual dust composition or size distribution, different from the dust grains in our own solar system. The holy grail of this analysis is spectroscopy. The James Webb Space Telescope is right now attempting to take the most detailed spectrum ever of an interstellar object. It will look for the infrared fingerprints of molecules, seeking not just water and CO, but rarer species like methanol, formaldehyde, and even amino acids. If it finds a molecule we've never seen in a solar system comet, or finds familiar molecules in bizarre ratios, the impact on planetary science will be profound. It will tell us that the recipe for making planetary systems is not universal, that the chemistry of life's ingredients might be more or less common across the galaxy. 3i Atlas, therefore, is a free sample return mission from an unknown star. Its value is incalculable, whether it is a quirky comet or something else entirely, because it offers a tangible piece of galactic diversity, challenging our parochial models of how worlds are born. The James Webb Space Telescope, JWST, is arguably the most important instrument trained on 3i Atlas. Since its launch, JWST has revolutionized our view of the cosmos, from the first galaxies to the atmospheres of exoplanets. Now it turns its golden eye upon a target within our own solar system, but of extrasolar origin. Its capabilities are perfectly suited to this task. Unlike ground-based telescopes that must peer through a blurring atmosphere, or Hubble, which primarily sees invisible and ultraviolet light, JWST operates in the infrared from the pristine environment of the second Lagrange point, L2. This is crucial because the heat signatures of molecules and the thermal properties of surfaces are most clearly revealed in the infrared. JWST's NIR spec, near-infrared spectrograph, and MIRI, mid-infrared, instruments are capable of performing a detailed chemical autopsy of 3i Atlas. They can detect the vibrational and rotational lines of water vapor, carbon dioxide, carbon monoxide, and other volatiles with a sensitivity orders of magnitude greater than any previous telescope. If there is a faint, transparent coma of gas that visible light telescopes have missed, JWST will see it. Furthermore, JWST can map the thermal inertia of the object's surface. A natural body of rock and ice will heat and cool in a predictable way as it rotates. An artificial object with a metallic shell or large, smooth panels would have a very different thermal signature, heating up and cooling down much more rapidly. JWST can also search for the telltale signs of industrialization, unexpected molecular absorption lines that could indicate polymers, plastics, or other manufactured materials. Every moment of JWST's precious observing time is a trade-off. While it stares at 3i Atlas, it is not looking at the early universe or a distant exoplanet. The fact that it has been allocated time for this target speaks to the immense scientific priority placed on solving this mystery. The data it returns in the coming weeks will be foundational, providing the most definitive evidence yet for the composition and perhaps the nature of this interstellar wanderer. In a remarkable twist of orbital dynamics, human technology will come closer to 3i Atlas than any Earth-based telescope. The European Space Agency's Jupiter Icy Moons Explorer, JUICE spacecraft, launched in 2023, is on a long, looping trajectory to the Jovian system. In early November 2025, its path will bring it within approximately 64 million kilometers of 3i Atlas. While this is not a close flyby in the traditional sense, for comparison, the Rosetta mission orbited Comet 67P from a distance of just kilometers. It is a unique opportunity. From its vantage point in deep space, free from the distorting effects of Earth's atmosphere, JUICE's instruments can gather data that is complementary to the telescope's back home. Its Janus camera system, designed to image the surfaces of Jupiter's moons, could capture high-resolution images of 3i Atlas, potentially resolving surface features or jet structures that are mere pixels to Hubble. Its UV spectrograph instrument could probe the coma in ultraviolet light, searching for atomic hydrogen, oxygen, and carbon, providing another layer to the chemical analysis. Most importantly, JUICE's particle environment package, designed to study the plasma around Jupiter, could be used to sample the solar wind in the vicinity of 3i Atlas. If the object is outgassing, even faintly, it will be creating a local disturbance in the interplanetary medium, a bubble of its own making that JUICE might be able to detect as a subtle anomaly in the solar wind. This is a classic example of serendipity in space exploration. JUICE was not designed to study interstellar objects, but its path through the solar system has granted it a front-row seat to one of the most intriguing astronomical events of the decade. The data it collects, even from tens of millions of kilometers away, will provide a crucial in situ perspective, helping to triangulate the truth about 3i Atlas from multiple angles and with multiple tools. The saga of 3i Atlas is unfolding in a new media landscape where the slow, deliberate pace of science collides with the instant, emotion-driven engine of social media. This creates a fundamental tension in how the story is understood by the public. The scientific process is built on a foundation of skepticism, peer review, and reproducible evidence. It moves methodically: observation, hypothesis, prediction, testing, and conclusion. It embraces uncertainty and is comfortable saying, "We don't know." The social media narrative, in contrast, thrives on certainty, drama, and simplicity. It latches onto the most exciting possibility, alien probe, and amplifies it, often divorcing it from the nuanced context of the underlying data. This creates a feedback loop where the speculation itself becomes the story. When scientists like Avi Loeb responsibly discuss the technological hypothesis as one of many possibilities, their nuanced statements are often stripped of their caveats and presented as declarations. This puts mainstream science communicators in a difficult position. How do they convey the genuine excitement and mystery of the situation without fueling sensationalism? How do they combat misinformation without seeming dismissive or being part of a perceived cover-up? We see this battle playing out in real time. In one corner, astronomers are publishing preprints, giving technical talks, and carefully wording their press releases. In the other, viral posts are stitching together data, assumptions, and narrative into a compelling but often misleading tapestry. The average person, seeking to understand what's happening, is caught in the middle, forced to navigate a confusing landscape where a YouTube video can have the same apparent authority as a NASA press conference. The story of 3I Atlas is thus a case study in 21st century science communication. It highlights the critical need for media literacy and the importance of turning to primary sources. It also shows the responsibility of scientists and journalists to clearly delineate between what is known, what is suspected, and what is pure, unadulterated speculation. The truth about 3I Atlas will be found not in the loudest voice, but in the quiet, persistent accumulation of data. The dark forest hypothesis, popularized by science fiction author Cixin Liu, provides a chilling, theoretical framework through which to view the 3I Atlas mystery. This solution to the Fermi paradox, "Where is everybody?" posits that the universe is like a dark forest teeming with hidden hunters, intelligent civilizations. Every civilization is an armed hunter, moving through the trees like a ghost, gently pushing aside branches that block the path and trying to tread without sound. Even breathing is done with care. The hunter has to be careful, because everywhere in the forest are stealthy hunters like him. If he finds other life, another hunter, an angel or a demon, a delicate infant or a tottering old man, a fairy or a demigod, there's only one thing he can do: open fire and eliminate them. In this terrifying cosmology, any civilization that reveals its location risks annihilation by a more advanced and necessarily paranoid civilization. Therefore, the only safe strategy is to remain utterly silent, to hide, and to preemptively destroy any potential threat that emerges. If one applies this logic to 3I Atlas, its behavior, if artificial, becomes deeply unsettling. A probe from a dark forest civilization would not announce itself with flashing lights and friendly radio messages. It would be stealthy, observational, and cautious. Its 1.4 GHz pings, if they existed, would not be a greeting for us, but perhaps a tightly beamed, encrypted report back to its home civilization, a whisper in the dark. Its trajectory, a distant flyby, is perfect for reconnaissance without engagement. It can observe our planet's biosignatures, our city lights, our radio leakage, and assess whether we are a potential future threat. The dark forest is not a proven theory. It is a grim speculation, but it is a logically consistent answer to the Great Silence. The fact that 3I Atlas fits so neatly into this paranoid framework, should it be artificial, is enough to send a shiver down the spine. It forces us to consider that the cosmos might not be a friendly place, and that the most prudent course for a young, noisy civilization like ours might be to learn, as the hypothetical hunters in the forest have, to be very, very quiet. The human fascination with and fear of objects from the sky is as old as humanity itself. Comets and meteors were long seen as omens, portents of disaster, or messages from the gods. The appearance of 3I Atlas and the ensuing speculation tap directly into this deep-seated archetype. In 1910, widespread panic ensued over the Earth passing through the tail of Halley's Comet, with entrepreneurs selling comet pills to protect people from the supposed poisonous gases. Orson Welles' 1938 War of the Worlds radio broadcast demonstrated how easily a narrative of alien invasion could trigger mass hysteria. In more recent times, the Y2K bug and the 2012 Maya calendar apocalypse showed that end-of-the-world anxiety simply morphs to fit the technological and cultural context of the age. The 3i Atlas story is a 21st century version of this timeless phenomenon. It combines our ancient fear of the sky with our modern understanding of orbital mechanics, and our burgeoning anxiety about our place in a vast, seemingly indifferent universe. The social media ecosystem provides the perfect petri dish for this anxiety to grow and mutate, amplifying legitimate scientific questions into existential threats. This historical context is vital for understanding the public reaction. The fear is not irrational in its origin. It is a primal response to the unknown, now supercharged by global instant communication. However, what is different today is our ability to respond with science, not superstition. Instead of sacrificing virgins to appease the comet gods, we are pointing the James Webb Space Telescope at it. We are not passive victims of celestial whims. We are active investigators, using the full power of our technology and intellect to understand the phenomenon. The story of 3i Atlas, therefore, represents a milestone in human evolution. The moment we began to transition from superstitious observers of the cosmos to engaged, rational participants in a galactic conversation, ready to face whatever we find with curiosity rather than blind fear. The detection of 3i Atlas confirms that we are standing at the dawn of a new field of astronomy, the study of interstellar objects, ESOs. With the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, set to come online, astronomers predict we could discover one such object per year, or even more. This will transform them from rare curiosities into a statistical population that we can study and classify. This nascent field is already grappling with fundamental questions. Where do these objects originate? Are they ejected from the outer regions of planetary systems by gravitational interactions with giant planets? Are they the leftover building blocks of planets never incorporated into a larger body? Or are they the shredded remnants of planets themselves, torn apart by tidal forces or stellar collisions? The answers will tell us about the dynamics and violence of planetary system formation. Future missions are already being conceived specifically to intercept an ISO. The European Comet Interceptor mission, for example, is designed to wait at the Earth-Sun L2 point until a suitable target is found, either a pristine comet from our own Oort cloud, or, excitingly, an interstellar object. Once a target is identified, the spacecraft would be dispatched to rendezvous and study it up close. For a truly compelling ISO, a dedicated rapid launch mission could be funded, carrying a suite of instruments to perform in situ analysis, perhaps even landing on it. The potential scientific return is staggering. It would be the equivalent of a sample return mission from another star system, but without the need for the long, difficult journey. The objects come to us. We could analyze their elemental and isotopic compositions, which carry the unique signature of their parent star's nucleosynthesis. We could study their structure. Are they solid monoliths or rubble piles? The discovery of a single amino acid on an ISO would be revolutionary, proving that the building blocks of life are not unique to Earth. The study of 3i Atlas is the proving ground for this new discipline, working out the methods, the models, and the questions that will define interstellar astronomy for the next century. In the fervent search for answers about 3i Atlas, it is humbling to acknowledge the vast expanse of our own ignorance. The unknown unknowns, the phenomena we haven't even conceived of yet, could be the key to this puzzle. Our entire framework for understanding the universe is built upon the physics we have discovered here, in our tiny corner of one solar system. What if the conditions in another stellar nursery, around a different type of star, gave rise to physical or chemical processes that are entirely foreign to us? We assume the acceleration must be due to either outgassing, a known phenomenon, or propulsion, an inferred one. But could there be a third option, a natural process we have never witnessed? Perhaps related to magnetic fields, quantum effects, or interactions with as-yet undetected components of the interstellar medium. Our models of the early solar system are constantly being revised by new discoveries. The concept of pebble accretion, where planets grow rapidly by accumulating small centimeter-sized objects, is a relatively new idea. What if interstellar objects are the pebbles of galactic evolution, and their properties are shaped by processes we are only beginning to model. Furthermore, our own instrumentation has limits. Our astrometry, while precise, is still measuring a faint dot from a distance of hundreds of millions of kilometers. Our spectroscopy can only detect what our models of molecular absorption can identify. There could be materials or structures on 3I Atlas that simply do not interact with light in a way we can currently recognize. The object itself is a messenger from a place with a different history, and it may be speaking a language we are not yet equipped to understand. The true lesson of 3I Atlas may not be a specific answer, but a lesson in cosmic humility. It is a reminder that for all our knowledge, we have just begun to explore the universe, and that the most exciting discoveries are often the ones that challenge our most fundamental assumptions, forcing us to rewrite the textbooks. Behind the headlines and the social media storms, teams of scientists are engaged in the painstaking work of deciphering the trajectory of 3I Atlas. A day in the life of an orbit modeler at JPL or the Minor Planet Center is a world of supercomputers, complex differential equations, and relentless attention to detail. Their work begins with the astrometric data, the precise right ascension and declination of the object measured against background stars from observatories around the world. Each data point is a small piece of a vast multidimensional puzzle. They feed this data into sophisticated N-body simulation software that models the gravitational influence of the Sun, all the planets, major asteroids, and even general relativistic effects. The program generates a preliminary orbit. Then comes the crucial step, analyzing the residuals. The modeler looks at the differences between where the object was actually observed and where the model predicted it would be. For a perfectly gravitational orbit, these residuals should be random, tiny fluctuations around zero. For 3I Atlas, they are not. They show a trend, a systematic drift that reveals the non-gravitational acceleration. The modeler's job is then to parameterize this force. They create a model that adds a constant radial acceleration, or perhaps one that varies with the inverse square of the solar distance, mimicking outgassing. They run the simulation again, over and over, tweaking the magnitude and direction of the force vector, trying to minimize the residuals. They must also account for non-gravs we know about, like the Yarkovsky effect, a thermal recoil force, and radiation pressure. This is a delicate, iterative process. A single bad data point from a telescope with a slightly misaligned clock can throw the whole solution off. The modelers are in a race against time, updating the publicly available orbit solutions as new data pours in. Their work is the bedrock upon which all other investigations and all claims of threat or safety are built. They are the silent cartographers of the solar system, and for 3I Atlas, they are mapping one of the most intriguing paths ever recorded. One compelling natural hypothesis that could explain the strange properties of 3I Atlas is that it is not a pristine, ancient comet, but a fragment, a shard from a catastrophic event in its home system. Imagine a planetesimal, a moon, or even a planet that was torn apart by a gravitational encounter with a giant planet or a passing star. Such an event would create countless fragments, some of which could be ejected into interstellar space. A fragment could have a very different composition and structure than a classical comet. It could be a piece of a metallic core, a chunk of icy mantle, or a section of crust. This could explain the high density and mass estimates. If it were a piece of a differentiated body, one that's separated into a core, mantle, and crust, it might have pockets of volatile ices sealed beneath a rocky crust. As it heats up near the sun, these volatiles could find a weak spot and erupt in a powerful, localized jet, providing the measured acceleration without producing a uniform, spherical coma. This exploding zit model of cometary activity has been proposed for some solar system comets. The unusual jet structure reported, possibly directed sunward, could be explained by a specific geometry of the vent on a tumbling, irregular fragment. The bluish color could be due to the composition of this excavated material, different from the surface. A fragment origin also makes statistical sense. The galaxy is a violent place. Collisions and disruptions are common. We may be seeing not the gentle wanderers of the void, but the shrapnel from cosmic disasters. This theory elegantly bridges the gap between the comet hypothesis and the anomalies. It allows for a natural explanation while accommodating the high mass, the strong but possibly episodic acceleration, and the lack of a massive classic coma. It suggests that 3I Atlas is not a representative sample of its home system, but a piece of its violent history, a tombstone sent adrift from a world that no longer exists. regardless of its ultimate classification, whether it is confirmed as a hyperactive comet, a strange fragment, or something that defies all categories. 3i Atlas has already secured its legacy. It has permanently altered our perspective of the solar system. No longer can we look at the space between planets as solely our own. It is a cosmic highway, occasionally trafficked by visitors from other stars. This object has been a catalyst, accelerating the development of new observational protocols, new AI-driven analysis tools, and new mission concepts aimed at these interstellar interlopers. It has forced a global conversation, both in scientific circles and in the public square, about what is out there and how we should respond. Its greatest gift may be the humility it instills. It has shown us that for all our knowledge, the universe still holds surprises that can stop us in our tracks and make us question our assumptions. The mystery of its acceleration, a tiny push in the grand scheme, has generated a colossal push in human thought and capability. As it recedes into the darkness after its December 19th passage, it will leave behind not just a trail of data, but a trail of questions that will inspire a new generation of scientists, engineers, and dreamers. The final chapter on 3i Atlas will be written in the observatories and laboratories of Earth in the months to come. But its true story is not just about what it is, but about what it has revealed in us: an insatiable curiosity, a capacity for wonder, and a relentless drive to understand our place in the cosmos. The sky will never look the same again. The hunt for the next visitor has already begun.